Alright, so far we've talked about dipole forces, or dipole-dipole interactions, and we've talked about hydrogen bonding. These are examples of intermolecular forces, and both of these rely on a molecule's partial positive being attracted to a partial negative of a neighboring molecule. And so we saw a picture like this when we were talking about dipole forces. The hydrogen is partial positive, the chlorine is partial negative. A different separate molecule also has a partial positive and partial negative, and the attraction of these two molecules is that intermolecular force. You can see that essentially what's happening here is that the attraction is between something that is positively charged and negatively charged, not full positive and full negative, but partial positives and partial negatives. This explains how we see liquids and solids in substances that have dipole moments, in things that have in polar molecules that are samples of substances, because since there is this force of attraction between neighboring molecules, as long as we get to low enough temperatures, this force of attraction causes the molecules to come closer and closer to each other and therefore condense into liquid if they were in the gaseous state, or even freeze into the solid state. Again, as you get low enough temperature, take away enough energy, get down to a low enough kinetic energy, that these forces of attraction cause the particles to be held rigid in the solid. But what about substances that are nonpolar? What about molecules that do not have a dipole moment? For example, let's take a nitrogen molecule, N2. Nitrogen is a diatomic element. That means there are two nitrogens. If we think of their Lewis structure, they happen to be bonded by a triple bond, and each nitrogen does have a lone pair. But as you can see, this is a totally nonpolar molecule. If I have a sample of nitrogen, I've got a bunch of these nitrogen molecules all floating around with no partial positives and no partial negatives. So what on earth would cause nitrogen, N2, to ever go out of the gas phase? And then my next question is it always a gas? We know at room temperature, nitrogen is a gas. But is there any temperature where nitrogen is a liquid? And absolutely there is. There is liquid nitrogen. This exists at very, very low temperatures. You're talking about in the order of around negative 200 degrees Celsius, nitrogen is going to be a liquid. Now, we actually can't get cold enough for nitrogen to become a solid, but in the liquid state, we know that the particles are very close together. So what is it about nitrogen that's causing there to be an attraction between the nitrogen molecules that would cause them to want to get close together and be held there loosely in the liquid state? It's not partial positives and partial negatives from a dipole moment, because nitrogen is nonpolar. So what is it about nitrogen that causes it to condense into a liquid? A nitrogen molecule has a triple bond, and each nitrogen has a lone pair, but in general we see a perfectly symmetric molecule for nitrogen. So I'm going to replace our Lewis structure with sort of a region of space. Here is the nitrogen molecule. It is three-dimensional, although I'm working on a two-dimensional sheet of paper. It is a three-dimensional structure. It's roughly spherical. And what we have in this spherical region at the very, very center, down here, really, really minuscule, are the nuclei for the nitrogen. That's where the protons and the neutrons are. And recall from our discussion of what an atom looks like, this takes up a very, very, very small amount of space. The rest of the space of this molecule is electrons. These are the electrons in the electron clouds for nitrogen. We know that they're in orbitals, and we know shapes of orbitals, but that's not important. Let's think of it as a roughly spherically symmetric region. Those electrons are moving. They are moving around the respective nuclei as well as between the nuclei. That's what attracts these two nuclei, is the bonds. Those are the electrons that are being shared. But at any given instant, there might be a buildup of more electrons on one side of the molecule than on the other. So at any given instant, there could be a temporary, instantaneous dipole moment for this molecule where the side that has the buildup of electrons would be partial negative, the side that has the depleted number of electrons, because they've all moved over to the right-hand side in my picture, has a partial positive. We call this an instantaneous dipole, and we know from our experiments that this is going on in molecules. Even molecules with permanent dipoles, polar molecules, exhibit this behavior. So we get what's called an instantaneous dipole, and all of the molecules in our sample are doing this. So we've got a bunch of molecules of nitrogen, and at any given instant, one of them might show this instantaneous dipole moment, which is going to influence neighboring molecules. So this neighboring molecule might see this partial negative charge, and then it would produce, or would be produced on it, an instantaneous dipole moment based on the attraction to the neighboring molecule. So at any given instant, we see these attractions happening. We call this an induced dipole attraction. The induced dipole attraction, we'll sometimes say it twice, just like we did with a dipole. We will call this an induced dipole intermolecular force. This is an intermolecular force. It is a force between molecules that aren't necessarily polar. They don't have to be polar. And it is based on an instantaneously induced dipole moment just due to the movement of the electrons in the electron clouds. As you lower the temperature on a sample of nitrogen that looks like this, again, you're slowing the molecules down, and these induced instantaneous dipole moments are more likely to influence neighboring molecules. Once you start slowing them down enough, these are going to influence neighboring molecules, and you'll get this chain reaction of a bunch of molecules lining up and being attracted to each other through these induced dipole moments. Now, just as quickly as these induced dipole moments occur, they also break, and so we see these happening and then unhappening over and over again.